Okay, everybody, we're going to get started. Next, we'll hear from the SRC Harrison group, the mentor Jill Burnham, and then we'll let our students take it away. Thank you.
Hi, I'm Rachel and this is Theo. We're interns in the Harrison lab and our mentor is Jill Burnham in the back. This summer, our main project was rewriting code related to the NuSTAR telescope.
NuSTAR, or the Nuclear Spectroscopic Telescope Array, is a high-energy X-ray telescope launched in 2012 from the Kwajalein Atoll in the Marshall Islands. It continues to operate over a decade later, observing objects such as galaxies, supernovae, and black holes. It was the first telescope to measure a black hole's rate of spin, and it was also a part of the Event Horizon telescope, helping take the first ever picture of a black hole. Right now, it's observed from the Barred Spiral Galaxy NGC 3783. Other targets it's observed in the past include supernova 2023 IXF, the Crab Nebula, the black hole in M87, and galaxy Centaurus A.
So this is the electromagnetic spectrum, and we're looking at some other telescopes compared to NuSTAR. And they're all X-ray telescopes, but you can see that Chandra and XMM Newton are both observing the lower range of the X-ray waves, more towards the ultraviolet end of the spectrum. NuSTAR, which is the first satellite to focus high-energy X-rays, is focusing more towards the gamma ray radiation lanes. So this graph shows NuSTAR's operating range and how it extends further than all the other telescopes. You can see that there's this big gap in the graph where Suzaku is not able to observe. Suzaku is the closest one in terms of range, and NuSTAR has a much higher energy ability. NuSTAR is actually focusing 7 times as much energy as Suzaku. So this all matters because different wavelengths are used to observe different objects in space. For example, radio waves are used to observe cool gas, and visible light is used to see the outside of stars. NuSTAR is using high-energy X-rays and almost gamma rays to see the remains of supernovae and the gas in galaxy clusters, as well as black holes.
ASICs are application-specific integrated circuits. They're custom designed chips for a particular processing task. They're commonly used for mining Bitcoin. NuSTAR's ASICs process the electronic charge signal from the cadmium zinc telluride detectors and send the data to an external microprocessor for transmission back to Earth. The ASICs are manufactured in groups and tested on the wafer, which is shown in the image, and then split up into the individual devices for use on boards. This is what a single device looks like when it's being, before it's put on the board. And then this here is an example of after it's been mounted onto the hydride.
This is a probe station, and we use this probe station to test that the ASICs on a wafer that were in the previous image are working. What we do is we put the wafer inside of the probe station, and we have a little map that tells us exactly where we are on the wafer when we're probing it. And then we put probes on it that connect the ASIC to a computer. Then we run 3 tests. The first test is the power-on test, which just checks that everything's communicating. It checks that the probe station and the ASIC and the computer are all working. Then we use the CP4V select test to choose an optimal 4V select value, which is accounting for variations in the manufacturing, because there are process variations. This is because the ASIC is kind of really big. You can see it, you know? It's kind of much bigger than some other chips, which are tiny. Finally, we run the full scan, which tests the full functionality of the ASIC, making sure it won't fail. But there's some other problems with the test. For example, the power-on test compares specific values to a range. And even if the value is 0.5% off, it gives you an error. So we need to manually go through all of this data, this output that you can see in the image, and make sure that an ASIC is actually okay. Sometimes the errors are real errors, like if a value is 3 and the range is from 9.00 to 9.01. But sometimes if the range is from 9.00 to 9.01 and the number is 9.012, then maybe that's okay. The CP4V select game is a guess the number game. It's really kind of fun, kind of boring, a bit time consuming. Basically, we use an oscilloscope, which measures the oscillations of voltage to see where the flattest line is. When we start, it looks something like this. And then we put in a value and we see it go like that. And when the slope is 0, that's when we have our number. We should be able to automate this, but instead we have to sit here and plug in different numbers to the computer. Trial and error. Also, in between every single test, we need to manually power cycle to clear the stored data. The goal of our project this summer is to fix all of these errors. We want to first rewrite the code. It's currently in Bash, and we want it in Python because it's so much more easy to read and easy to edit. And we want to also try to automate some of those annoying processes that we have to do by hand, such as the power on test. We could have a computer that allows more room for error instead of manually going through all the data. We also want to create a graphical user interface that's a little more user-friendly.
Another intern, Eddie Chang, wrote an API for a power supply that will let us power cycle from the computer and automatically store the value for the current. Right now, this is done by hand. Eventually, we want to automate this all 3 tests from start to finish with minimal interaction or minimal error checking. Any progress that we've made comes with a lot of errors. Bash and Python have very different programming styles, so it makes translation difficult. As our oscilloscope was borrowed for use on another project, we are currently working on making a more friendly user interface in Python using PySide6.
But while we're doing all of this, we're also doing some other fun things in the lab. For example, we're sorting parts with another intern, SRC Harrison, and we're cleaning drawers so that it's easier to get to the parts and other things in the drawers around the lab. We're sorting through and sometimes recycling some papers. And while we're doing all of this, we're just learning how it is in a lab. Like when lab people are doing lab things in a lab, it's super exciting. But not only that, we also found some really cool software or hardware, old hardware, such as this PowerBook computer. That's so old. It was from 1994, but it actually says on it that it was made in 1904 because there's a glitch. It's that old. But the laboratory we're in is about 40 years old, and so this was actually used in the beginning of this lab.
We'd like to thank a few people for working with us through this entire process. Eddie Chang for writing the code for the power supply.
We'd like to thank SRC Harrison and Julian Du for being just fun interns with us. It's been really fun.
Joseph Biggle for just any programming assistance we need. Hiromasami Asaka for writing the original code in Bash for the Coke Station in 2010. Varun Palarao for writing part of his thesis on new stars detectors, which we referenced while we were working on this project.
We want to thank Alessandra Signorini for helping with the probe station tests and answering our questions.
We want to thank UC Berkeley for continuing to operate New Star today.
We want to thank Fiona Harrison for both launching New Star back in 2012 and also letting us be part of the Summer Research Connection today.
And then last but not least, we want to thank Jill Vernon for always being an amazing mentor. Thank you, Jill.
Any questions?
One more thing, but open source tools that we used include Sigwin, Python, Tyvisa, PSP tool, PySide6, and then Bash shell. Just wanted to give like a shout out to that. Now we'd like to open it up for questions if anybody has any.
What did you find that surprised you this summer in terms of the experience and what you were expecting before you started?
Sure, yeah. So when I started this summer, I kind of didn't really know what I was gonna do. I talked to Jill and tried to figure out a good project. And then I got here and Theo was able to help me with figuring out how this was working. I'd never actually seen Bash code before, but Theo knew all about it and was able
I
to.
didn't know.
Yeah,
Yeah. No, I've been working as an intern here for over a year now. I've worked on a few projects with it, and this is the longest, I mean, it's been 6 weeks, the longest long-term project that I've been working on. I really enjoyed it. And it's still definitely a work in progress. It's gonna take more time to continue rewriting rewriting the code base for this, but I'm looking forward to continuing to work on that.
Are you both, are either of you envisioning a career in astronomy?
I am, yes. And like astronomy or astrophysics. Yes.
I do have a question, but I really enjoyed your talk. I think it was really clear and easy to follow, and it looks like you had a good time. But I also wanted to comment that for friends not at all. I programmed in Portugal.
But yeah,
Great job.
thank you. We really appreciate that.
Have they put that Apple computer on eBay yet?
I got that from you. Actually, it's part of the collection.
Oh,
Yeah.
oh, I thought that was one you found. No, that was. Oh, okay.
the other one, the kind of box off the side with what that's.
We throw it out the laptop, we use it if we need my whole software. Yeah. Awesome. Thank you, everybody.